Hey, what's up, guys? This is John, and today let's take a look at this LeetCode problem. 1562. Find latest group of size m. So this is one of the weekly contest problem. Okay, so I mean it's a medium, but to me I feel like it's more like between medium and hard. At least I didn't solve this problem during this weekly contest. I had a hunch that I should use the union find, but I didn't have time to finish the coding. So yeah. Anyway, let's take a look. Given like an array that represents the permutation of numbers from 1 to n, okay, and you have a binary string of size n that initially has all its bits set to 0. Basically, at the beginning, for example, if you're given like a five arrays here, five elements here, right? So which means you will have like five zeros at the beginning. And at each step, the position, the index at the 3 here, one base will be flipped to 1. For example, this one here, 3 is 1. So the first time, the 3 will become 1, then the third number, okay? And in the second step, 5 means the fifth element will become, sorry. So the fifth element will become 1 here. And same, so on, continue. So at third step, the first one will become 1. And at fourth step, the second one will become 1. And the last step, 4 will become 1. Okay. So, and then the question is very interesting. It asks you to find the latest step at where there still like exists at least one group of ones of ones of the length m here, of length exactly m. For example, the the this in this example, the m equals to 1, which means we need to find the last step that still has at least one group of ones. See at the beginning here, right? So the first one is 1 here. When after the second step, we have two group of 1. At third step, we have 3. But when we at fourth step, you know, once we flip the bit to 1 at the second place, basically this two ones will be merged into a 3 ones, which only leaving us only one group left. And when it comes to the last step, everything will become one group. Okay, so that's why the answer for this example is 4, because at the step 4, we still have uh, one group of 1 left. But at step 5, there's nothing. There's no group of 1. Okay. So uh, and for this example, we're looking for like a group of two ones. Okay. But if we follow the sequence of this array here, there's no way we can have like two ones at any step. That's why we return -1. Okay. Um, I mean the easiest approach, not approach. I mean the more intuitive thinking is like we can use union find, right? So it seems like union find. For example, this one. So when we reach flip this one here, basically we union the left and the right together, right? And yeah, I think that's a good start. I think union find can definitely solve this problem. We just need to modify the union find a little bit. I mean, if you guys still remember the template of the union find, basically we have a parent, right? And then we have a rankings. We have ranks. Basically, uh, I mean the ranking is not that important. Basically, we use rankings to determine like which subtree we need to merge to the other, right? Basically, the, the part with the smaller ranks will be merged to the part with the higher ranks. That's how the union find works, right? And then, but for this problem, in besides the union find itself, we also need to maintain like the counts. Uh, Basically, we need to also remain the counts of each of the groups here. I mean, basically, we're gonna have like a group count, like group count. So basically, this group count means that we need to maintain like how many like for one, okay, how many ones the count of each consecutive ones. Since we have like in total we'll be having like 5 ones in this case, right? So basically the index the index will represents with this many ones, how many counts we currently have, okay, and we'll be using this one, right, basically to maintain the at each step, uh, what's the groups, what's the counts of that many ones, okay, and so that this is the main structure we'll be using because so that if we somehow can maintain this variable, right, and then after each step, right, we simply can check if the group counts m, right? I mean m is the length we need. If this one is greater than 0, okay, as long as this one is still greater than 0, then we know okay, we still can meet our requirements, right? So we just update the step, and once we finish everything, then we know the the latest step will be our answer. Okay, cool. And but how can we update, right? How can we maintain this group count? So since the index is the count itself, right? In order to maintain this one, we also need like another count here. Another count. Basically, the count is for each of the root of the union find. I mean in terms of the union find, right? Basically in the union find, we have different roots, and this count will be the basically the size of that union of that tree, the union find tree. Okay, and we'll be using that one to update this group count. Uh, cool. And so let's try to code these things up here. Okay. I mean, the coding itself is not trivial. Basically, it's a little bit long because we need to maintain like the unified structure. Okay, so stay with me, guys. Okay, I'll try to code faster here. So basically, the first thing is we're gonna have like for the union find, we have two methods right here, x, and we have a find and we have a union. Okay, union is x and y. Okay, so, and for the union find, we also need the parents, right? Remember? So at the beginning, each of the parents it's itself, right? Which means we're gonna initialize this thing with the range of n, right? Basic, it's just part of the union find template, okay? And then we have a ranks, okay? Ranks equals to 0, 0, and n, right? So these two things are just a very basic union find thing. How about we just implement the very basic union find templates here? Basically, for union find, while doing the union find, while doing the find, we also do the path compression. Okay. If you guys don't know what the path compression means, you can try to look for some like different videos online or try to search on Wikipedia. Basically, every time we have a sorry when we have like we're looking for a length of variables here, right? When we try to find, let's say for example, this is a root. Okay. Anytime when we have a like root here, we're trying to find what's the root of this node here. So by the time we're traversing back to the root, we remove any any of the nodes on our way to enter this one. Let's say 1, 2, 3, and 4. Okay, basically we'll be moving the 3 and the 4 here, 3 and 4 here. Okay, so this thing is gone. This is also gone. So after this one, right? So the next time we search 3 and 4, there we don't have to traverse back here, right? We can just we're gonna basically find the 3 and 4 in O1 instead of ON. Okay, that's the basic idea of the path compression. And the way we're doing it is like basically if the parents x is not equals to x, why we're doing this, right? Because at the beginning, right, the the root itself, it's its parent, right? That's why we're using this one. And then the parent x equals to find parents x. Okay, so only these two lines can help us do that. It's very powerful. And in the end, we return the parents x. Okay, basically you're using a recursive call here. Okay, and then for the union, right? For the union, there's a root one, and we find x. Okay, and the root two union find y. Okay, so and if r1 is not equals to r2, okay, because if they're the same, there's no point of union. It means that they have already been union before. Okay, we only union when they don't have the same root here. Basically, the template is this. Basically, if the rank R1 is equal greater than the ranks of R2, okay, and then we assign the parents of R2 to R1, okay, and the ranks of R1 will be increased by 1. Else we do the opposite. We assign the R1 the parents of R1 to R2, and then we also do a ranks of R2 plus 1. I mean here the equal sign here, right? So it doesn't really matter if the ranks are the same. We can either do this or do this. In this case, I just happen to be doing this one. Okay. Yeah, I mean, cool. So basically, that's the basic of the union find. You know. Uh, yeah. So that's that. But in order for us to solve this problem, like I said, we need some other data here, like the group. We need the counts. Okay. The counts is the count for each of the roots. Okay. And at the beginning, the count for each root will be 1. This is kind of easy to understand, right? Because at the beginning, each of the root has 1 count. Okay. And then we have a group count here. Either group counts or like, yeah, you can call it group count here. 0 and I think the group count is also, let's see. For the group counts at the beginning, it should be 0. Yeah, it should be 0. Okay, and we have a n plus 1. Yeah, so why we're doing n plus 1, not n here? Because the count is the index, right? And the count is 5. And in this case, the most count is 5. Okay, that's why when we have a group count 5 here, the n is 5, right? But if we're doing 5 here, we'll be out of the boundaries. That's why we do a n plus 1, because the count is 1 based, whereas the n here is 0 based. Okay, so uh, so once we have how are we going to utilize this to at least to help us maintain that, right? Basically, I mean, when we union the x and y, and we have R1 and R2, okay? Remember, the count itself represents the count of that root, right? Okay, and we have a two count here. You know, after we union this two roots here, basically, I mean the group counts of those two roots will be decreased by one. Okay, right? What I'm say means is this, like basically the counts of that, right? So the counts of the R1, right, will be decreased by one because those two subgroups is gone basically when we let's say we have one here, and then we have another one here, okay, and then we add a one here in right in the middle, okay. So after adding this one here, right, I mean here we have a count of two, here we have a count of three, right, and after union this two parts with the one here, right, we'll be having like a six here, right? So the new group is six, and after we getting a new group of six, okay, we know we lost a group of two and a group of three here. That's why we need to decrease so for example, this is the two group by one. Same thing for the other groups, okay? R2 by one, okay? And yeah, and also, you know, since we merged that, this is the final one, but we also need to update the counts here. Okay, so what does the count mean? The count means the count of the basically the root one of the counts equals to root two will become the counts R1 plus counts of R2. Oh, I'm sorry. Okay, actually here I think this example is not a very good one because here we're only merging like two parts. Yeah. So there won't be any of this part. Basically only this part. Only the only the only this side. Uh yeah, so basically so we will have three here. So the one is one, right? So the one is here, and then basically we'll be losing the group of one, the group of two, but we're getting a group of three. Okay. And yeah, and after that, right, since we have a union those two groups, right, the counts of the R1 and R2 should be the same, right? Because they should have all have the same counts, which is the sum of the R1 and R2. Okay, and now let's add that the new combined group here. Okay, R1. Okay, plus plus one, right? Because at this moment, since the R1 and R2 are the same, it doesn't really matter like which one we'll be using. We can use either one. Cool. I mean, that's basically how we maintain this group count here. Okay. Okay, so now we have that structure set. Let's do an answer here. So let's try to do the main logic here. The answer is this, right? We start from minus one and we do a step and then the index, okay, in enumerate array. The value here is 3 here, but remember, I mean, the first thing we need to do is that we have to convert this index to a 0 base. Remember, this thing is like it's 1 base, right? 3, but we since we only allocate n space here, that's why we need to do a index minus 1. I mean, if you don't want to do this, I mean, I think you can like change this thing to a n plus 1, n plus 1, and n plus 1. Okay, but in this case, I'm still keeping the zero base index here. Okay, uh, cool. So let's see what's next. Okay, so now every time when we have a number here, right? It's a one. It means that the groups the group of counts of 1 will be increased by 1. So that's the first thing we need to do here, because every time we have a 1, we know, okay, it's a group of 1. Okay. At this moment, we have a new group of 1. Okay, cool. So, and now we will try to uh, uh, mm, we will try to union with the left side and the right side. Okay, so for the left side, we have to check the index, right? Basically, if the index -1 is still greater than 0, then we know, okay, we can go to the left side. But how can we know if the left side is 1 or not, right? Basically, let me think. We have to know three. Yeah, basically we need another another like array to tell us, okay, if the left side or the right side has already been set to 1. Okay, we can simply have a visited one here, right? So false to n. Okay, and we'll be only union when that thing is, or we don't if we don't use visited, we can also maintain like array here. We check if that position has a 1 or not, but the true or false will also work. Okay, or like or we can do this like uh, current, what's the value here? Current string. Okay, we can also do this. Current string. Okay, so and we check if the current string, if that's the index, I'll do an I here. I think index is too long. I it's shorter. Okay, so if this index, right, is 1, right? So if this thing is 1, then we know, okay, we can union those two. We union the uh the I and I minus 1. Okay, same thing for the other side. I select to n and current string I plus 1. Okay, oops, is 1. Then we also union that, right? We also union the I and I plus 1. Okay, so after that we just need to uh yeah, so first let's make these things I equals to 1. Okay, so we set this one to make for so that the next one can, we set the current one to be current position to 1. So we mark, right, there's a 1 at this position. Now at the end of each step, we simply check if the groups counts of the m, right, it's still greater than 0. Yeah, or we can skip that. And then we update the answer, step plus 1. And then in the end, we simply return the answer. So here, step plus 1 is like, since the step is 0 based and the answer is 1 based. Okay, right? That's why we do a plus 1 here. Mm, yeah, I think that's pretty much it is. Okay, let me try to run this code. Okay, cool. So this one passed. Submit. Oops. Oops. Uh, out of index. Hmm. Uh, ranks R1 and oops, sorry, R2. Missing an R there. Yeah, cool. So it passed. I mean, uh, yeah, I mean, this one is like, it's not very easy one. Definitely not an easy problem. I mean, it seems like, using the union find is a little bit overkill, because as you guys can see, we have a lot of like code just to maintain this union find, but it's definitely a good solution. I mean, so basically, okay, just to recap real quick, we use the union find template, but besides the union find, we also maintain like this group counts by using these counts here. Basically, every time we union two parts, right, we uh we lose those two counts first, right? And then we get a new, instead we're getting a new bigger counts. That's why we keep the counts for each of the subgroup, and then we union them together, and then we create a new counts, a new group counts. And here we just using that structure and try to check the value here, the group count value. Mm, okay, so that's that. Actually, there I'm going to talk about another uh, easier or concise solution here. Actually, that one uses a similar like concept, but it has much lesser code. Uh, okay, cool. So for that one, actually the idea is this, like basically we have a 1 1, right? And then let's say there's like another side. This is the left side, okay? And this is the right side. Let's say 1 1 1 1. Okay, so this is the right side. Okay. So the idea is like, now let's say we have a 1 here. We have a 1. We're adding a 1 here. Basically, now we're actually uniting those left side and right side together. Okay. And actually, it's using the similar like concept here. We're still maintaining like a counts of the group here. Okay. But instead of using union find, we simply update that, because at this moment, let's say the left side, the count is 2, okay, and the length is 2. On the right side, the length is 4, okay. And by uniting these two lengths together, right, we have like what? We have 7, yeah, right? We have a 2 plus 4 plus 1, which is 7, okay. So same thing, right? Basically same thing here. So for the in this group count here, basically we'll be removing one. We'll be removing decrease the number for 2 by 1, decrease the number uh 4 by 1, but we will be increasing the number of 7 by 1. Okay, so that's similar. Okay, now the question is, how can we get the left side length and the right side length? Okay, so that's the question we need to figure out here. And in the union find, we used a root, right? We use a root to get the length of the left side and the right side. But here, I mean, the brilliant the trick here is that uh, on each basically on for example for each of the sub array, right? For each of the sub group here, actually all we need to maintain is the starting point and the ending point. If we can just have the latest up-to-date length value for the starting and the end, then we can easily find that. Because why is that? Because when we try to find the left side, right, we're looking at the last element of the left on the left group, And when we are finding the the length of the right side, we're looking at the first element of the right group. Okay. So for that, every time when we have like this one, we have this left and right, and we update it, right? Now, all we need to do is we simply need to update the left side, the left this one. We just need to update the first element and the last element of our new combined group. Basically, all we need to do is just update this one to 7, and we also update this one to 7. Okay, because the next time, right, no matter which one will be using this subgroup, it can be either added to here or one here, right? We can either like combine from here, or we can either combine from this side. But either side, right, whenever they're looking for the length from the start or from the end, they will always get the 7. Okay, so that's the trick here. Basically, we don't have to update all the length in the range in between. Okay, all we need to care, we only care the starting point and the ending point. Okay, cool. So with that being said, let's try to code these things here. uh Basically same thing, we need a length of array, right? That's the length of array, and then we'll be getting we'll maintain a length. Okay, basically that's the group. uh mm, let's do a count, right? So basically the first one will be the counts. Okay, so the counts is 0 times, here we do a n plus 2. Okay, and then we have a group count here, right? We have group count, it's basically the 0 times n plus 1. Okay, so why we're doing like n plus 2 here, because we'll be looking for, okay, basically first we'll be traversing from the first one to the last one, and every time we'll be looking for the left side and the right side, right? So in order to make sure that our index will not go outside of the boundaries, we will be adding one buffer on the left side and one buffer on the right side, so that it won't it will never go out of the boundaries. That's why we do n plus 2 here. So here for the n plus 1, I have already explained that, because the index here is the counts. Okay, is the counts. So that's why we do n plus 1 here. So now, okay, we have an answer, of course, -1. Okay, so now we just need to loop through this array here. So we have I, the right step, and the I, and then enumerate, same thing here. Okay, so that's that, and left, right? So the left side, we have the left count, or you can call it the left. Okay, let's do a left count here. Counts I -1, right? Remember, so because at this moment, actually, for the left subgroup, we're using the last element from the left parts. Okay, and the right count is the count, the I plus 1. So for this one, for the right part, we're using the first element of the right part to get counts. Okay. Now, actually, the new counts, right? So the counts of the actually now the counts of the so now we need to form the new count, the new group, right? And the first element in the new group is this, right? It's I minus left count. Okay, right? Because if let's say if there are two ones on the left side, and our current is I here, right? So the beginning of the new group will be I minus left count, okay? And the end of the new groups will be I uh, plus right count, okay? And we update those to the start and end by by combining the counts, okay? Right count plus one, right? Yeah. Now let's update the group count here, right? So the group count is the actually we'll be losing the original counts, right? Which is the left counts, okay, right? By one, and we'll also be losing the right counts by one, okay? But instead, we're getting a new group count. We're getting a new group count of we can use either one, yeah. The count of I. Let's use the beginning, right? The beginning of this new group plus one. Okay, yeah. Here we can either use I minus this, or we can use this one because they have the same value here. And same thing here, right? Basically, we just do a if group counts m, right? And then we do to answer equals to step plus one, okay, right? And in the end, we simply return the answer. Okay, let's try to run this. Yeah, so this one passed, submit. Yeah, as you guys can see, this one is like it's faster than the union find. So why is that? Because as you can see, you guys can see, so the space complexity for this one is O of n, right? Because we only loop through it once, and here it's just a O1, right? And the space complexity is also O of n. But for the union find, so what's the complexity of union find? First we have this ON here, okay? But on each step we have a union. So what's the complexity of a union? Okay. Oh, first we do a find. We do a we do a find, and the complexity of the find we usually consider it as O1. So I think I briefly discussed about that earlier, because even though the first find will be O of n, but since we're doing this path compression, the next time will be O of, so the next time when you look for the same x, it will be O of 1. And when it comes to amortized, right, amortized time complexity, we consider this one to find to O of 1. And what else? Uh, we have these things here. We do that. Well, basically, this thing is like, it's just it's more than O of one, right? I mean, it's a little bit like uh, log n maybe. Yeah, I'm not quite sure about the complexity of this the union here, because we do a two finds, and then we do a union. I think this part is obviously O of one, but the union part is like, I mean, this part is O of one, but the find part is uh basically it's more than O1. Maybe O log n. Maybe. Yeah, but okay, but for this one, it's strictly O of n, because we don't have that. We don't need to maintain this union find the tree structure, right? We don't have to maintain this root here. We simply just maintain this two group here by marking the beginning and the end to the with the new length, okay, so that we can be use it later on, because Again, so when we look for the left side, we use the end of the left subgroup, and when we are looking for the right count, we're using the start of the right group. That's why we have to update both the start and end in the so that later on when the new group got merged, both sides will have the correct length. Okay, cool. I think that's yeah, that's pretty much I want to talk about this problem. Yeah, it's very very interesting problem. Yeah, okay, cool. Thank you so much for watching the video, guys, and I hope you guys learned something. Yeah, and stay tuned. And okay, see you guys soon. Bye bye.